Good morning, sir.
Good morning, Ashley.
How are you,
How
sir?
are you?
I'm good.
I think I'm on time. I had a little bit of a problem with my laptop, so I will have a little difficulty in my presentation sometime because
Okay.
I'm just made up the presentation just now. So excuse me for that because I think something happened to my original laptop, so I'm using another computer. Because of Mac and Windows, there is a
Okay.
little issue in PowerPoint. So
Okay.
some visuals may not be so clear because of that thing. But I hope I have actually managed most of it. It's a change in platform. Windows has a different PowerPoint and
Yes,
Mac
yes,
has
yes.
a different PowerPoint. So now I am using a Mac. So
Okay.
hopefully I should not have much problem. I hope so.
If you like to share the PPT, you can share so that we can play from here also. But
No, actually, it is
you
not.
can manage.
Once it gets saved in Mac,
Okay.
some resolutions are lost and some fonts are lost.
Okay.
So
Okay.
I hope that is not going to affect. That's the thing.
Okay. Okay, sir.
The audience are students and faculty.
Students, faculties, and research students.
Huh?
MSc students we have, faculties we have, and research students also we have.
Okay. So I go from basics to the application. So I'll see. It's 1.5 hours, right?
It's
With
1 hour.
1 hour, 15 minutes.
1 hour followed by discussion.
Okay. So you want 1 hour? Okay. So it may exceed a little more than 1 hour. Maybe.
No problem, sir. No problem. Yeah. You want to play the PPT and see?
Yeah, I'll share. One minute. I think I have to do some accessibility.
You all please go to the lab.
It's working, sir.
It's working, right?
Yes.
Yeah. I have to see whether I'll have the laser pointer or not. That is something which is what I need to see. And I should title use presenter view show and I think I may not be having a pointer, but I think I can use this. You can see my mouse, no?
Cursor, we can see your cursor moving.
Yeah. Right. Yeah, fine.
Okay.
Some chat, something is there. Please record the session. Okay. Usharan is asking.
Yeah, once we start, we'll record.
Right.
Yeah.
So you have most of the things online, or is it you are having classes offline also?
Currently, we are having online classes.
Online, okay.
Yeah. Sir, I think we have 8 minutes more. So we'll wait.
We'll wait. Yeah, definitely.
Yeah.
You take a break. So it is working. So I'll stop sharing now.
Okay, sir.
Yeah. So I'll I am around, so you don't have to worry. I'll come back and I'll just keep my video off and this thing. Yeah.
Okay, sir. Sure. Yeah.
Is my voice is clear?
Hello?
So shall we start the program?
Yeah.
Okay. A happy Tuesday morning to all of you. We had two wonderful sessions yesterday where we learned about the fundamentals of teaching as well as fundamentals of chemistry. The current session onwards, we are going to be focused on the main theme of the FTP, that is the
Good morning,
fundamentals
Uba.
and applications of spectroscopy. To begin with, we have one of the best Raman
Hello.
spectroscopic scientists in India,
Harish?
Professor Chandrabhas Narayana, who is having more than 3 decades of experience in Raman spectroscopy. Professor Chandrabhas Narayana is highly energetic, ever smiling, and a very friendly person to everyone. Today, Professor is going to talk about the basics and applications of Raman spectroscopy. I'm so grateful to you for giving your valuable time in spite of your busy schedule. Thank you so much, sir.
Thank you. Thank you.
In continuation, today afternoon at 2 o'clock, we will be having another lecture by eminent Professor Netaji Muniratnam, who is going to talk on X-ray crystallography basics and applications. I hope you all will enjoy the session today. To introduce sir formally, I invite Dr. Vasant Kumar Bhaskara, Department of Chemistry Biochemistry, MS Ramaya College of Arts, Science and Commerce. Over to you, Vasant sir.
You're muted. You're muted, Bhaskara.
Sorry for that. A very good morning to everyone gathered on this platform for the second day of FTP. Today, it is my pleasure and I feel privileged to introduce the speaker of our today's morning session, Professor Chandrabhas Narayana, Director of Rajiv Gandhi Center for Biotechnology, Trivandrum, Kerala. Professor Chandrabhas received his PhD from Indian Institute of Science, and then he was a postdoctoral fellow and visiting scientist at Cornell University, United States. He was also a visiting professor at University of Paris and Marie Curie, Paris. Then Professor Chandrabhas has relocated to Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru. He served at various positions, starting as assistant professor, then associate professor, dean, and chairman of chemistry and physics of material unit at JNCR. Currently, Professor Chandrabhas Narayana is at Rajiv Gandhi Center for Biotechnology as a director, and he also served as Dean of Research and Development at the same place. Dear participants, hold your breath to listen to Professor Chandrabhas Narayana's exhaustive accomplishments and caliber in the field of spectroscopy research. He has guided several PhDs and published nearly about 190 research papers in the journals of high reputation, such as Nature, Cell Press Journal, Advanced Functional Materials, Advanced Materials, Proceedings of National Academy of Science, USA, Physical Review Letters, and so on. He has 4 chapters in books and holding 3 international patents. Professor Chandrabhas is a fellow of National Academy of Sciences, India, Royal Society of Chemistry, and Indian National Academy of Sciences. His research accomplishments have been felicitated with prestigious awards like Material Research Society of India Bronze Medal in 2007, Sir C.V. Raman Young Scientist Award from Karnataka Government in 2008, CNR Rao Oration Award in 2009, Shiksakar Rak Cam Senior Fellow in 2016, MSRI ICSC Superconductivity and Material Science Senior Award in 2017, Mijushima Raman Lecture Award in 2018, Platinum Jubilee Lecture Award of the Indian Science Congress in the year 2020. Professor Chandrabhas Narayana is the editor for many international journals and is a member of the Corporate Advisory Board of Reva University, Bengaluru, governing body of the Government Science College, Bengaluru, member of the Board of Studies for St. Joseph College, Christ University, MS Ramaya Institute of Technology, Reva University, and Calicut University. Sir, it's really an honor for us to have your talk in our FDP program. I extend my sincere thanks for accepting our invitation. I hope everyone is eagerly waiting to listen to your talk. The session is over to you, sir. Thank you.
Yeah, thank you. Thank you so much, Vasant Bhaskara, for
Thank you.
introducing and giving a real exhaustive account on my accomplishment. Thank you so much. And first of all, I should thank Ashley to be pursuing me and getting me on board on this one. You know that as heading an institution, it becomes a little difficult with our times. But I was very happy because I've been associated with MSRIT for a long time. So this is another arm of MS Ramaya Institute. So I'm very happy to be associated with this FDP program. So now I'll share my screen and let me know if you're able to see the screen. I hope you are able to see my screen, right?
Yes, sir. It is visible.
Yeah. So since there are MSc and PhD students, so I thought that I should start from basics, and I will actually tell you my latest work. And Ashley warned me that I will have only 1 hour. I'll try as much as possible to finish in that time. But the idea is that this is one discovery which was made in India. And this is one science Nobel Prize we got. And I always feel that people should know what it takes to do this spectroscopy. And it's a very important spectroscopy because it can be used in not only physics, biology, and chemistry, but it is there are a lot of applications of this. And there are many things you can do with this particular technique. And it's a non-contact based technique. So it is very easy to use in situ studies also. So with that, let me start by saying what Raman spectroscopy is and how do you do these experiments, and then show you some examples from my research. So when we talk about Raman spectroscopy, it is a light matter interaction. So most of us know that when light falls on a material, the things which happen is well known to all of us, like transmission, reflection, then you have absorption and luminescence. And many of the talks are related to these aspects, which in spectroscopy you use, like absorption and luminescence, which means fluorescence, photoluminescence, various other things come under luminescence. And absorption is another technique which is very strongly used. Most of the times, these two are very commonly used. And of course, along with that major thing, what happens is transmission and reflection. But interestingly, along with this, there is something which is very, very important, which happens is elastic scattering. And this is something which happens every time. And when I say that if I see you, or when you see a material, it is because of the elastic scattering, you will be surprised. Even though the scattering is a very weak phenomena, but it still is the reason why we see each other. And this, I would leave it as an assignment to all of you to understand how elastic scattering is the reason why we see each other. Elastic scattering, when I say, you should remember something which is taught to you in 12th standard or 10th standard, which is elastic collision. Elastic collision, when we talk about, it means the energy is conserved. That energy remains same after the collision. So elastic scattering is also the same, that energy remains the same. So in terms of light, energy means h nu. So the frequency remains the same. That means the color of the light remains the same. So elastic scattering is when light falls on it, it gets scattered in all 360-degree directions, and it is all over the place. It is different from a reflection because it doesn't have that Snell's law followed in this case. But along with this, we also have some shifted frequencies coming, which is called the inelastic scattering. And whenever we talk about inelastic collision, we know that the energy changes. And this change in energy is in light is considered as blue shifted or red shifted. So that's why I've given it as blue and red, but it doesn't mean that green becomes blue or green becomes red. It is red shifted or blue shifted in that sense. So this is what is the important thing which Raman discovered. And that gives you information about the molecules and atoms which are present inside a material. And it is a lot of information which you get about its environment, various other things happening to the system. So it's become a very important tool. As I was saying, scattering itself is a weak phenomena. It is very, very less. But if you compare inelastic scattering, that is the shifted frequency, which we are talking about, you can see the ratio we are working with. If 10 to the power of 7 photons are elastically scattered, only 1 photon out of that gets inelastically scattered. So we are actually working with a very, very weak phenomena. So Raman is a very weak phenomena. And that was one of the reasons why Raman actually took a long time for it to become useful. And it was only after the advent of lasers, which was in 1960, Raman spectroscopy became a laser Raman spectroscopy. And now recently, it has become much more easier because the Raman spectrometers have become much more easier to use, and they are very easily available. And that's the reason. And when we talk about Raman, it is basically we are talking about the molecules. So when light falls on it, it actually excites the molecules. And when it de-excites, it doesn't come back to the original ground state. And that is the reason for the shifted frequency which we are seeing. Now, Raman can be of 3 different types. So the molecules can do rotations. So you can have rotational Raman. Molecules can have vibrations. That's called vibrational Raman. And they also have electronic transitions. So it can have electronic Raman. All 3 types of Ramans exist. And we generally are going to concentrate on vibrational Raman. And we will not concentrate on rotation and electronic Raman in this talk. But these also exist in nature. So all of these things have energy. So rotation has energy, vibration has energy, electronic transitions have energy. So these energies are absorbed from the light or taken away from the light to show you these shifted frequencies. And that's the reason why we see these shifted frequencies. To demonstrate that it does happen, we have taken a monochromatic light source. And when we take a, monochromatic light source, and this, in this case, it is a blue light. And you can see that when the intensity of the blue light is too much, it looks like white. And that is because your detector gets saturated. And that is the reason why it is looking white. It is not white light here. It is an intense blue light coming out of the laser. When it falls on dust particles it's a dark room, so the dust particles are getting illuminated. And that is the elastic scattering coming from the dust particles. Now, when I pass it through a transparent liquid, the light should have gone through without getting deviated. But you can see a lot of light coming 90 degrees to the direction of the beam. And that is because of the elastic scattering. And it is so intense that your detector gets saturated. And that is, this liquid is cyclohexane, which is a transparent liquid. Now, Now, if I actually filter out the blue light, that means elastic scattered light, if I filter out, then you immediately see a different color coming out. And this is the red shifted light, which you are seeing here. And so we can actually see this is the inelastic scattered light, which is not too weak. It is also quite strong, you can able to see. And this is the reason why Raman could discover it, because in organic molecules, especially organic liquids, your Raman scattering is very strong. And that is what he did. Most of his experiments were done using organic molecules. And that's how he could discover this Raman effect. And this is the shifted frequency. And this shifted frequency is very, very important because it tells you about the molecule present inside the system. Now, we can actually make miniaturized Raman spectrometers. So we can take a laser, which is available in Amazon. Green lasers are available for 1,000 rupees. And you can take a filter, which filters out and makes it monochromatic. And then you pass it through a liquid. And then you filter out the elastic scattered light and collect it using a fiber. And once you collect it through a fiber, you can actually disperse it using a grating and a mirror. And then you can take a photograph using an SLR camera. You can see, once you actually take a photograph, you see the elastic scattered light. And then inelastic scattered light, you can see coming from this molecule. And this is what is, if you digitize it, you actually get peaks. And wherever the light is coming, you will get a peak. So this is the peaks, which are shifted peaks, which are actually telling you. So the energy between this is the energy of that vibrations of the molecule itself. So this is what we are actually looking at. And we have developed our own setups here in both Bangalore, and now I'm developing it in Trivandrum, where we make our own Raman spectrometers. This is the collection in optics. And you have a small monochromator here, and then you can attach it to a computer and you can actually record samples, Raman spectra. So this is a miniaturized version of it. You can take it to a biological setup where you can have a 96 well plate or 396 well plate, and you can actually put it inside this and do biological diagnostics also in this thing. And that's the reason for developing these spectrometers. And to show you that these spectrometers are not really bad, I have shown you a spectra, which is brown spectra is from my samples, my system, and green spectra is from a commercial setup, which is actually costing about 1 crore and above. And you can see that this setup is exactly same in both in intensity as well as in looking at the spectra itself. And you can the only difference here you can see is that they are lower resolution, which I will be talking about what you mean by lower resolution. So you can see there is a complete matching of how the spectra looks like. Now, just to put in perspective, what is Raman fluorescence and IR? Actually, Raman is looking at, so you know that in your Jablonski diagram, you will have S1 state, S0 and S1 states. These S1 and S0 states are coupled with vibrations, and you actually have transitions from either to intermediate states and coming back, or going to all the way till excited state and coming back, but not coming back to the same ground state, gives you the Raman scattering. And that is a very sharp signature. But if it doesn't happen like this, and if it actually goes all the way and comes down and comes on all the vibrational levels, then you get the fluorescence from the sample. If this happens to be a fluorescing sample, and this fluorescence peak is about 100 nanometers width. And you also see if you excite this fluorescence, you always get Raman peaks on top of it. So vibrational Raman is always seen on fluorescence peak, but Raman is a very weak phenomena, so it is a very, very tiny peaks on top of it. In case of IR, you do not actually supply the energy higher than the S0. So we exactly supply the vibrational energies, and that gets absorbed. And these absorbed energies are the ones which give you an IR. So IR and Raman are actually complementary to each other because they look at the same vibrational levels, while fluorescence looks at the electronic levels in the system. Now, to tell you how many vibrational modes will be existing in any molecule, it's a very easy calculation which you can do. So generally, if you have n atoms which are not connected to each other, each atom's motion can be described in 3 directions. So when an atom, because atom is a very tiny system, it doesn't have any size, or it is a very, very infinitesimally small point. So because of that, whenever an atom moves, any movement of the atom can be described by X, Y, and Z. So there are 3 directions in which it is described. So degrees of freedom is 3 in the case of an atom. But when you have 10 atoms, then it is 3 into 10, because 3 different directions for each atom. So 3 into 10, that is the total degrees of freedom. So that is how we talk about 3n as the degrees of freedom to describe a motion of a particular atom. But the moment atom is actually combined together, it loses that freedom to move only in that direction. It also starts getting connected to each other. So when it moves, if the other one is not moving, then it actually starts to have a rotation, or it can have vibrations associated with it. So this connection actually is the reason. But that means this number of degrees of freedom cannot actually get lost. This number of degrees of freedom should remain. So there are three things which happens. One is translation. If all the atoms move in X direction, all the atoms move in Y direction, all the atoms move in Z direction, then it is the translational motions. And this is the three translational motions which can be existing. We can also have rotational motion. In general, rotation can be in X, around the X-axis, Y-axis, and Z-axis. So three different directions it can have rotations if the molecule. But the problem is that if suppose that all the atoms are connected in one chain, like linearly, when it gets connected linearly, what happens is that its rotation along the direction of the axis where all the atoms are connected is not definable, because the atoms are very, very tiny. It's like taking a infinitesimally small wire. So it doesn't have a rotational degree of freedom in this direction. So whenever you have a linear molecule, then it will not have three rotations, it will have only two rotations. So basically, linear molecules will have two axes only, while rest of the molecules will have three rotational degrees. So now if you look at 3n minus 3 from translation and 2 or 3 from the rotation, then the remaining number of degrees of freedom becomes vibration. So that's how you can calculate the number of vibrations. So for any linear molecule, it is 3n minus 5. And in case of a non-linear molecule, it is 3n minus 6. So these are the total number of vibrations you can calculate. So this is how you can find out how many vibrations exist. Now, when you have a diatomic molecule, what happens is that you have two atoms and degrees of freedom is 3 into 2, 6. And the total number of translations possible is 3. So 6 minus 3 is 3. And total number of, because it's a linear molecule, it will have two rotations. So if you remove it, only one vibration exists. And that vibration is, for any diatomic molecule, the vibration is symmetric stretching. This is the only vibration possible in diatomic molecule. Now, you can see here I have taken HF and HCl. So one atom is the same. One other atom is actually heavier than the Cl is heavier than the F. And you can see when heavier atoms are there, then it actually has a sluggish motion. So this vibration is lower energy compared to this vibration, which is higher energy. And you can easily see, I have written this in terms of centimeter inverse, and you know that centimeter is a length quantity, but inverse of length is what I have given it as here. Generally in spectroscopy, especially in IR and Raman, we use centimeter inverse for a long time. But it is easy to convert it, because you know that 1 by lambda is also related to frequency. And if you multiply with hc, then you actually get Planck's constant times speed of light. You actually get energy, h nu. So that is why this actually becomes 8,000 centimeter inverse is roughly 1 electron volt. And that means this is roughly around 500 milli electron volts, and this is about 300 milli electron volts. So the energies of vibration generally are between 50 or 60 milli electron volts to about 500 milli electron volts. That is the energy scale of vibrations. This is the energy which happens. Now, as soon as I add one more atom to this, you can see that I have not added it in linear sense. So that is why it looks like this. Any molecule which has the shape of AB2, which is like this shape, will have only this kind of vibrations. So this one I have named it as water, but you can have any other molecule which is AB2, which will have only these molecules. Now let us look at how many vibrations should exist for this. You will immediately see 3 into 3 atoms are there. So 3 into 3 is 9. And if you remove 3 translation from that, that means 6. And you have, it is non-linear, so 3 rotations possible. So 6 has to be removed totally. So that means it is having 3 vibrations. And that 3 vibrations is equal to 3n minus 6 is equal to 3 vibrations. And that is given here as symmetric stretching, asymmetric stretching, and symmetric bending. And you can see in asymmetric stretching and symmetric stretching, the bond length is changing, while in the case of bending, it is the bond angle changing. And you know that it is easier to have the angle changed compared to the bond stiffness because of the stiffer bonds. So this is higher energy compared to lower energy. So bending always is lower energy, and stretching is always higher energy, which is very easy to see. Now I add one more atom, and in this case it becomes ammonia or any AB3 kind of a molecule in the pyramidal shape. It will have same vibrations, and this is NH3, and you can see immediately how many vibrations should be there. You know that 4 atoms, so it has to be 4 into 3, that is 12. 12 minus 6 is 6 vibrations, but we have only 4 vibrations. The reason for this is because you can see that this molecule looks more and more symmetric. And the more symmetric they are, then many of the vibrations become more or less, most of these vibrations would actually collapse onto each other, because if it look at different directions, they look the same. So that means there is degeneracy. So there are degeneracy here and degeneracy here, because if these two are bending, you could also have these two bending and these two bending. So any of these things will look the same. So they are degenerate. So that's why degeneracy is existing, while these are not degenerate. So this is symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. So this is, so all vibrations can collapse onto 4 different types of things: symmetric stretching, asymmetric stretching, symmetric bending, and asymmetric bending. Now, if I go further, I will actually add a molecule like octahedral molecule. And you know, octahedral molecules are very, very symmetric molecules. If you look at from all 3 different directions, it looks exactly this. I have taken SF6. Any AB6 type of molecule will have only these vibrations. And so this is symmetric stretching, this is asymmetric stretching, this is asymmetric stretching, and this is symmetric bending, this is asymmetric bending, and this is asymmetric bending. So now you can see that these are degenerate, these are degenerate, and this is not degenerate, this is not degenerate, this is single value. And that is the reason why we should have had many more vibrations in this case, because there are 7 atoms. So 3 into 7 should have been 21, and 21 minus 6 should have been 15 vibrations. And you see here only 6 vibrations. So many of these vibrations are collapsed onto each other. So that is degeneracy. Now, one more thing, very importantly, I said, if the molecules have same shape, they will have similar vibrations. So that means this becomes like a fingerprint. So I can actually know what is the kind of bonding which is present in the system. So I can know the structure of the molecule also by investigating vibrational spectroscopy. So IR and Raman becomes very useful to know the structure, whether you have formed this molecule or not. Have you done the substitution or not? The moment you have a symmetry removed, then it becomes degeneracy is lifted. So the number of peaks will increase. So immediately, if the number of vibrational modes are larger, then you know that it is not a symmetric molecule. This is a very easy way to find out. Now, how does light actually interact with molecules and then create vibrational modes? This is what we need to understand, and for which you do not need to go beyond your 12th standard electrodynamics knowledge, which you have studied in charge and vibrations and all those things. So when you talk about a simple harmonic oscillator, if you take a 2-ball and a spring, all of us have studied in our simple harmonic oscillators that the frequency is related to the spring constant and the reduced mass. root of that. Okay, so reduced mass is given by this fraction. So this is known to us as simple harmonic oscillator, 12th standard we have studied. We do not need to go beyond that. Okay, so now similarly, a diatomic molecule having a bond and two atoms here. So it is exactly like a two-ball system. So that will have a frequency associated with it, and that frequency can be given by this model. But the only difference is that when you look at the atoms, atoms are not just a solid body. It is actually made up of electrons and nucleus. So that means there is a charge. But in general, they are charge neutral. There is no charge associated with a molecule, but they still are made up of charges. So when electric field is applied, and you know that electric field is an oscillating function, so I can always depict it as a cos or a sine. So what happens is that you have a cos function. So it is an oscillating function, and it has dependence on the frequency with time and space and momentum. That's what is given here. So basically what happens is that you have a frequency of the what is the oscillations of this, as well as when it moves in space, how the vibrations actually travel. So that is what is given here. But generally light travels at speed of light, which is very, very fast compared to the molecule, which is doing a Brownian motion. So while the light falls on it, the molecule is not at all moving. So you do not have to consider henceforth this position part of it, only we'll look at it. Now, when an electric field falls on the molecule, immediately you know the charges are going to be affected. So the only charge which can be affected very easily is electron, because electrons are very light matter compared to the nucleus. Nucleus is thousands of times heavier than the electrons. So electrons will move. So when electric field is in this direction, the electron will move in this direction, and if the electric field is in this direction, the electron will move. So an oscillating electron electric field will produce the electrons to move in this direction, and that means you are actually creating an induced dipole. And induced dipole, because now positive charge and the negative charge is separated, so you have created a dipole, and this dipole is actually dependent on the electric field which is falling on it, and there is a proportionality constant which is called the polarizability. How easily the electron can be moved around, that is the polarizability of it, and that's why this is actually the function. Now when you substitute back, you can see that it is actually oscillating with the same frequency as the frequency of the electric field, and that is the elastic scattering. And you know that from your 12th standard that any oscillating dipole produces electromagnetic radiation, and that's what is basically the reason for the elastic scattering. Now this is true if alpha was a constant. What is the problem now? Because when electrons are actually moved, if the atom starts vibrating, the electron will have to follow that vibration. So that means this polarizability of the electron is a function of the vibration, and that's what would happen. So alpha is a function of the vibration, and vibration is given by a coordinate. So it is actually having a frequency associated with it. And now when you expand it, this is not like the atoms are moving like this. Atoms are moving very small, tiny amount. So it is a small vibrations, and any small displacements can be written in Taylor series. So basically the Taylor series is the way you expand it, and this is in Clark's table. If you go and look at it, you will find the Taylor series here. So alpha is now no longer alpha alone. Alpha is actually a function of this vibration, and you can see that this vibration is very, very tiny. So I do not take into consideration higher terms. But if I take the higher terms, then it is second order Raman, third order Raman is what would come from this thing. So this is the first order Raman we are talking about. So this is it. Now when you substitute it back, you will see that you suddenly have two frequencies associated with it. One is this frequency of the light which is coming, and the frequency of the vibration and the system. So that's just I have substituted here. Now, you all know from your trigonometry, cos A into cos B can be written as cos A plus B and cos A minus B. So I have just done that, and suddenly I see there are three different frequencies coming. One is the frequency which is actually the frequency of the light. This is the elastic scattering, and this is the inelastic scattering. One is less than the light frequency and more than the light frequency. So this is the blue shifted, and this is the red shifted. So this is a Stokes-Raman and anti-Stokes-Raman. And now this happens for all the vibrations, because each vibration is independent of it. For every vibration, you will have two such one blue shifted and one red shifted. So this is what is the Raman scattering, which is happening. And the selection rule is basically, if this is slope of a displacement, right? The polarizability with respect of the displacement. So if I plot the polarizability as a function of the displacement, then if I am looking at equilibrium position, so if the slope happens to be 0, that means it's a maxima or a minima, then it is actually considered as Raman inactive, because this will be 0. So this will not exist. But if it is non-zero, then it will be Raman active. So this is the selection rule. So as far as everything is concerned, this can actually explain how Raman happens. So basically, there is another interesting thing which happens is that Raman and IR, I told you, are complementary. So when we look at it, IR and Raman, you can actually look at it. So you can either do IR or Raman. But that is not true. If a molecule is symmetric, if the molecule is symmetric, then you can see that all the IR modes are not present in the Raman. Raman modes are not present in the IR. So it is mutually exclusive. So these modes are not having same origin. So they are different. So in a sense, we have to do both IR and Raman if it is a symmetric molecule. I removed the symmetry of the benzene by adding this. It is an indene. And you can see immediately all the IR modes are matching with the Raman modes. So basically, what it means is that when the symmetry is removed, IR and Raman are having similarity. That means they will exist at the same time. So basically, whenever you have a symmetric molecule, then you need to be careful that you should do the IR and Raman separately. But if you have a non-symmetric molecule, then you can actually go ahead and do only one of the techniques. Now, I said the selection rule was perfectly all right. But what happened is that when we look at dou alpha by dou Q, which I was actually mentioning here, it is same. So the intensity of the Stokes and anti-Stokes should be the same. But this is where we actually have a problem, because it is quantum mechanical. Electrons are quantum mechanical particles. The energies are quantum mechanical. So you cannot just be having the same thing. So if I would have actually done the experiment, I will find that Stokes is always stronger compared to the anti-Stokes. That is what happens. And this is because of the fact that excited state has lesser population compared to the ground state. And that's the reason for this. Now I will actually go ahead and show you now whatever I wrote as the dou alpha by dou Q in classical, I have expanded that in quantum mechanics. And temporarily, I do not want to go into the detail of the quantum mechanics. I am only expressing this, and I will tell it in physical sense. So what exactly these mean, because in quantum mechanics, you use Hamiltonian, and Hamiltonian has been defined here as electron radiation interaction. This is electron phonon or electron vibration relationship, and this is electron radiation. So that is the meaning of it. It's a third order perturbation. So there are three. This is a. It is actually giving you a real value. So it is basically a probability of finding such a thing happening. So that is a thing, and there are three Hamiltonians, so two energies associated with it. That's the simple explanation of it. Now to explain that, this is going to explain to you how Raman shift is dependent on whether it is Stokes or anti-Stokes. So now I have separated out the ground state, electronic state from the vibrational states. So you have vibrational ground state and excited states. Now when light falls on it, it immediately absorbs. And now we have always been taught that it should have an energy state present, otherwise it cannot absorb. It has to be absorbed, so energy states should be present. But here we don't know what energy we are supplying. So how is that there is an energy state? But you should realize in quantum mechanics, when you excite a molecule, immediately the eigenstates, whichever were there, they will combine and form a linear combination of it temporarily. And that means the light can be absorbed. And that's what is called the virtual state, because we cannot see them really. And it is like if you do an optics experiment where you have a convex lens, you see an image, but you cannot actually touch it. That is the virtual. So it exists, but you cannot measure it. So these are linear combinations of all the eigenstates which are present. So it is only present when you excite the molecule. So as soon as you excite, the molecule gets these energy states and they can actually absorb. But because they are very short life, it immediately comes down, giving out the same light. And that's the elastic scattering. But because there is a strong coupling between the vibration and the electronic states, when it is excited, it could actually give energy to the vibration. So it can go from ground state to excited state. And that is through the electron vibrational coupling or electron phonon coupling. Phonon is for lattice, which is what is. So when now it comes down, it is redshifted. So this redshifted light comes out. Now, this is the Stokes Raman. But along with that, another thing can also happen is that excited vibration can come down to ground state, giving energy to the electron. And now it comes down, it is blue shifted. So this is the blue shifted light. Now, you know that the population of the excited state is less than the ground state. So this is more probable compared to this. So that is why the Stokes is much more stronger compared to the anti-Stokes. And that's why most of the times we are always looking at the red-shifted light or Stokes Raman, not the anti-Stokes Raman. But it also has another interesting thing. If suppose these energy states happen to be real, then these energy states become blows up, because there is a probability of this matching perfectly. And that means you have resonant Raman effect. And that I will show you in experiments later. Now, intensity of Raman peaks depend extensively on various complex ways. One is the polarizability of the molecule. Another is the intensity of the source, and also the concentration of the active groups present. And as well as it is dependent on the wavelength of the light, and it is related to the power of the Raman is related to the fourth power of the frequency of the source. All of these things actually come in to tell you how the intensity of the light Raman's peaks will be. And so usually it is directly proportional to the concentration of the sample. So generally, if the intensity increases, that gives you an idea that for a particular wavelength of light, for a particular energy of the light, and for the molecule, the intensity increase is directly related to the active groups. So it can be a quantifying tool later. Another interesting aspect happens is that laser lights or any wavelength of light has polarization associated with it. And the molecular vibrations or the polarizability of the molecule, electrons, are also highly dependent on the polarization of the light. Because the electric field is like this or electric field is like this, it determines how the polarizability will be affected of the Raman. So in a sense, Raman, when it is done with a plane polarized light, it actually is highly dependent on it. So we can actually do an experiment like this. The scattered light will have all polarizations, but we can actually select the polarization. This is called parallel polarization because this is the polarization of the light and the polarization we selected. This is parallel polarization. And this is called the perpendicular polarization, where it is perpendicular to it. So you have, if you take the ratio of this is called the depolarization ratio. If this ratio is independent of the direction of polarization, that means if it is 1, then it is highly depolarized. If it is less than 0.76, it is called polarized. And you can see that it happens in certain cases. And this is very important thing. So when we look at it, most of the symmetric vibrations are highly polarized, while asymmetric modes, are not polarized in the sense. Now, here is an example of polarization dependence. So I have taken carbon tetrachloride. I have done the Raman with parallel polarization and Raman with polarization, which is cross polarization. You can see that this is a symmetric vibration, and you can see highly depolarized. This peak is not even seen, while these are all asymmetric modes. So basically, they are not polarized at all. They are depolarized. So you can see the effect of polarization on the system. So you have to be very careful to understand what kind of vibrations they are. Now, I have taken this for a specific reason. I have taken carbon tetrachloride. You know that it has 5 atoms. So the number of vibrations it should have is 3 into 5, 15, minus 6. That means 9 vibrations, but it has only about 4 vibrations. This is degeneration, lifted. So this is the 4 vibration. And any AB4 molecule, tetrahedral molecule, will have this kind of a vibrational peak associated with it. So you can easily know whether it is a tetrahedral molecule or not, by looking at it. And each of this is actually related to a vibration. You can see this is the symmetric vibration, symmetric stretching. This is asymmetric stretching. This is symmetric bending, and this is asymmetric bending. And that's basically it. Now, I want you to carefully look at this peak. It should have been a single peak, but what you see is that there are some wiggles here. And whenever you have a spectroscopy, whether it's NMR, it is IR, photoluminescence, any of those things, if you really want to know if there are multiple peaks, you just lower the temperature until unless there is a phase transition or something. You can actually see the width of the peak reduces, so you can see more detail. So I have reduced this peak, and suddenly I see there are 5 peaks associated. 1, 2, 3, 4, and 5. What is the reason for this? It is because chlorine actually exists in 2 isotopes. So that means there are 4 positions of chlorine, and you have 2 types of chlorine. And the relative abundance is quite good because this 75% of chlorine is 35 and 25% is 37. So you have enough chlorines. So you immediately see that these higher frequency means lower mass, and so lower mass is there. Higher frequency is means lower mass, so it means Cl35. So all 4 are Cl35. Then this is the one, and then you have Cl37 one. That is the most abundant part. So this is the tallest peak, and now you can immediately guess this is 2 Cl37s. And here it is 3 Cl37s and 4 Cl37s. And the intensity is low because this probability of having more Cl37s is lesser and lesser. So it immediately tells you that isotope effects are there. Now you would have immediately asked, what about carbon C13 and C14? You know that the relative abundance of carbon C13 and 14 is very, very low. So you need whole large number of atoms to even see it. So isotope effects are very easy to see. Now, I'll quickly tell you how it is useful to use vibrational spectroscopy for getting informations easily. Now, you know that you have methanol and ethanol, and without taking out, can I actually tell whether it is a methanol or ethanol in the bottle itself? So here you can do that very easily. You just put a laser light and you actually do the experiments on that. You know that the only difference between ethanol and methanol is this CH2. And the moment you have an additional CH2, you immediately have CCO stretching, and you also start having CH2 deformations and others. And immediately you see the emergence of new peaks. And so you can immediately say, this is ethanol and this is methanol. So it's so easy to find out without actually opening. Now, another interesting molecule is, you would have heard about this recently in Bombay. There were many cases where people were actually finding MDMA. The MDMA is a ecstasy, which is a party drug, while it is made from this particular molecule. This is the primary molecule, and you can see the difference in the peak. This is singly substituted benzene. This is triply substituted benzene. Immediately, the symmetric stretching of That is basically the breathing mode of the benzene is lost. And that is given by 1000 centimeter inverse peak. And you can immediately see this peak is disappeared. So by just doing this, you can know whether this is the primary compound or this is it. So if you are making this compound, you can easily see whether the compound has actually formed or not without even doing any other experiments. You just look at it, you can immediately see. Most of the peaks remain the same. You can see most of it remains the same, while because all the peaks are coming because of this, the peaks due to this and removal of this is the one which has the distinguishing factor. So it's very easy to say. Here's another example of a tetrahedral molecule, and I told you the spectra should look similar. And if you one look at it, looks like it looks similar to the carbon tetrachloride spectra. The only difference is the degeneracies are lifted. You can see the degeneracies are lifted because SO4, all 4 bonds are not the same, and hence there is the degeneracy lifting. But it is still a tetrahedral molecule, so you can actually see that. Now, you can see that the 2 atoms attached to it, one is magnesium and another one is sodium. And you can see both of them are attached to SO4, and this is the vibration of SO4. Now, why is that the peaks are shifted? The reason is this is like a Coulomb force, Mg2 plus, whereas this is Na1 plus. And this Coulomb force and SO4 2 minus. So basically, that Coulomb force is able to dampen this and it is reduced. So you can immediately know whether it is MgSO4 or sodium sulfate by looking at this shift itself. Similarly, if I have a geometric isomer, so here is a molecule which is actually a very important molecule because it works for asthma, while this is a pseudoedephrin, which is basically this chiral molecule is the reason for it. And this is not working for asthma, but it works for cold. So these 2 molecules are produced from a plant. And you know that they are produced in 50-50. Now, if I want to know whether I have isolated this completely, then how do I find out? If you see, this is having a singly substituted benzene. So I see this is present in both of them. But the moment I look at very carefully this peak, the intensities are reversed. The intensities are reversed. So you know one is, so the chiral molecules will have intensity reversal, and you can easily find out one from the other. Otherwise, if you quickly look at it, it looks identical. But when you look at those peaks which are associated with the chiral molecules, you can immediately see the intensity ratios are opposite, totally opposite. And that gives you, so geometric isomers also you can find out without actually opening the box, you can actually see that. So it's very easy. Now, another interesting thing is here, you all know that diamond is the most toughest material. But when diamond occurs in nature, it is actually present in sand. So there are inclusions which can happen because sand is nothing but SiO2. So there can be calcium silicate, which is laranite, which can be included in the sample. So here is the calcium laranite. This is the laranite, and this is the diamond. Now you can see that when you have included, you can do Raman of the diamond. And one of the best way to know whether it is a diamond, other than the jeweler saying that it is a diamond, you just have to do the Raman of the diamond, because sp3 hybridization is there, and sp3 hybridization gives you a very strong peak at 1332 for diamond. And that 1332 peak is the only peak which is present in the Raman, and that is what signifies it is diamond. Now, when I do a mapping of the diamond, you will see most of the places it is 1332. That is the black. But as you come closer to the laranite, you start seeing there is an increase in the frequency. Now, increase in the frequency shows here that there is as you go closer and closer to the laranite, the diamond peak is becoming very, very close to 1338. Now, you can do an experiment where I take the diamond and squeeze the diamond. When I apply pressure, I actually can shift. And this pressure is about 27,000 atmospheres, 2.7 gigapascals, which is 27,000 atmospheres. So basically, the presence of the laranite inside the diamond is stressing the diamond to around 27,000 atmospheres. And you know that 27,000 atmospheres is a huge pressure. And this is what happens when you actually take one atom and put inside another place where it should not be present. That is why doping effects come. So chemical pressure, it can actually create. So you can find out chemical pressures with Raman very easily from these kinds of experiments. So Raman is a very powerful tool in that sense. And another example is crystalline to amorphous material. As soon as you have a crystalline material, you have sharp peaks, while amorphous material, just like in X-ray, you will have broader peaks, and you can immediately know whether it is an amorphous system or not. So these are very easy to do, and here is in two solutions. So you have a solute and a solution. You can easily find out the concentration by looking at the intensity, because the solvent remains the same. You can see the intensity drops, and you can plot it, and you can find out the intensity. So what is dissolved inside, you can find out the concentrations very easily. So whenever you do a Raman, you have to be very careful that you need to have these four quantities measured accurately. That is peak position, peak shift, bandwidth, and intensity. These things should be accurately measured, and it all depends on the laser excitation, reduction of stray light, collection optics, spectral resolution, and spectral coverage. And all of these things are very important in determining this accurately. And I will give you a quick example. So any Raman spectrometer has a laser which is monochromatic. It falls on the sample. It produces both elastic scattered light and inelastic scattered light. You filter out the elastic scattered light, and then you use a dispersing medium to disperse it and take a photograph. This is basically what happens in a Raman spectrometer. So now I wanted to show you what happens if I have a molecule which has S0 and S1 given, and if I take a wavelength of light which is below the S1, it is equal to S1 and it is above S1. What will happen? Now I have taken this example of hand cream. You use the hand cream. I just do most of them are aromatic in sense. So they have aromatic molecules, and they generally have absorption in the range of 400 to 500 region. So they actually give out some fluorescence, which is basically in the red region. So this is the red region fluorescence. So if I were matching with S1, you can see it exactly matches with the fluorescence of this material. So I have taken a red light and 633, and you can see it's more dominated by the fluorescence, and the Raman is sitting on top of it. It is very weak. But if I take 785, which is lower than the S1, then you see the green light, you get very beautiful Raman spectra. But the moment I go above this, then I am closer to 473. And you know that 473 is closer to the pi star interactions. So all the CH stretchings are getting expanded very strongly in aromatic compounds, CH stretching, because it's related to the pi star interaction. So you can see resonant Raman effect here, which is happening because you are closer to the pi star interaction. So resonant Raman effect is seen very strongly in these systems. So it is very dependent on the wavelength of light. Another thing is, if I have a transparent sample and if I have a opaque sample, how do I use it? If I use a micro Raman, then it is good for opaque samples. You see, micro Raman works very nicely because if I take a 100x objective, I get more stronger peak compared to a 10x objective. You get it. But if my sample is transparent, you can see that if I use a 100x, my sample signal is lesser compared to the if I take a long working distance, low objective lens. So that gives me stronger. So whenever I am using a transparent sample, I should not use a high magnification lens, but I should use a low magnification lens to get very good signal from a transparent material. So this is another interesting thing. Again, another important thing is, can I resolve peaks very well? And that depends on the monochromator. And any monochromator is set of lenses mirrors and a grating present in it. Now, what happens if I have the focal length of the spectrometer? That means I have a bigger spectrometer or a smaller spectrometer. You can see when I have a bigger spectrometer, the green is smaller spectrometer and 800 is the bigger spectrometer. So you can see the resolution. You can immediately see you are able to resolve better when you have a bigger spectrometer. So is this the only way you can do it? If you don't have the money to buy it, you can also do it by using different gratings. So if I actually look at 600 grating, which is green, 950 is red, and 1800 grating grooves per millimeter is the grating, I can see that 1800 gives me a much better resolution. You can see peaks which were not visible before. You can see here, there is only one peak here, whereas there are two peaks in this one. So higher gratings also for the same spectrometer length, I can actually increase the spectrum, this also. Another important thing is penetration depth of the laser, how deep it can go in. I have taken silicon and I am showing the penetration depth in that. As I go to higher and higher wavelength, the penetration is more into the sample. And what is the effect of it? I will show you. So here is silicon, pure silicon, on which I have actually put silicon germanium. It's a detector. So I actually grow a feeder layer, and then I grow little more silicon germanium, which is very uniform, and then coat it with silicon again. Now this silicon is not matched in lattice with this, so there will be strains in there. Now, if I do with 785, my spectra looks like this, mostly silicon and silicon germanium. That is what I would get, because that is the major concentration. It is there, pure silicon and this thing. But because 488 doesn't penetrate more than few microns, it doesn't go up to the silicon. Immediately, I lose the silicon spectra. I start now seeing another peak here, which is related to the strained silicon. Now, if I use UV light, then it doesn't penetrate more than nanometers. So I only get the silicon, but not the silicon germanium. Now you can see, I can actually get what is the strained layer of silicon present. And I can map it to find out how the strained layer is there. Is it uniform or is it actually having some issues? We can actually image it. So you can do a Raman imaging of the samples to find out on an interface or any other place, we can actually get information. Another important thing is because we use microscope, it is confocal also. So you can actually see if the samples happen to be transparent, you can actually know what is present inside that. So you can see here is a nylon embedded inside polyethylene, and polyethylene has a different spectra, while nylon has another spectra, and you can actually map it and you can find out the thickness of nylon present inside without actually cutting it. You can exactly know what is the things present. Now, what I have shown is that there are many things you can do with Raman, many examples where it can be used, and all of these things you will be encountering in your life for research. So next, I will actually quickly go, I will not go to this example because this is more on the perovskites, but I will just quickly show you how I can actually show you magnetization effects in a system. Just one example, latest work which we are doing. So we were looking at, these are systems like samarium ferrite or these rare earth ferrites are very important because if you look at it, they have applications in use of storage material and various other applications. So people are interested in actually being able to reverse this by applying a magnetic field or applying a temperature or heating it or any of those things, you can actually get it. So one of the important things we were looking at was the spin reorientation transition, which is seen in samarium ferrite. Okay, so what is these are all rare earth orthoferrates, which are a class of compounds very strongly studied because they are multiferroic in nature, and most of these multiferroic systems have very interesting properties later. But here is one example where we do see a spin reorientation transition, because generally they are going into a antiferromagnetic state. But as you lower the temperature, they tend to cant, and that is giving you a little ferromagnetism in the system. But there is a flipping of antiferromagnetic to ferromagnetic, and spin reorientation can happen. And this is something which is very interesting in these systems. Now, what you see is that you can have samarium ferrate and yttrium ferrate. Yttrium being a it's not a F electron system, so it is actually not having any spin reorientation transition associated with it, because spin reorientation transition happens because of the rarer atom ordering with respect to the iron atoms. That's what leads to this. So yttrium doesn't have. Now, when you actually dope them with yttrium, you actually are causing a shift in the reorientation transition, and that's what the objective was. So if you look at it, suddenly you see there is a spin reorientation transition happening in this system around 300 Kelvin after the Néel temperature, which happens to be above 500 degrees centigrade. So we were interested in knowing what is happening, and you can see it is anisotropic, because if you apply the magnetic field along B and along A, it reverses the the magnetization, completely reverses the magnetization. So the magnetization is higher here, magnetization is lower here, while it is anisotropic. So this anisotropy, we were looking at it, and from the magnetization study and the structure study, we could see that it is actually going from gamma 2 to gamma 3 magnetization. Now, this is gamma 3 is not allowed in ferrates. It is not allowed. And this is the second case where magnetization in gamma 3 is seen in the system. So we wanted to understand the microscopic picture of it. So what we did is we took two crystals, one crystal grown along the B axis, another one along A axis, not grown. The crystal is cut along A and B axis. And you can see that if you do the Raman, it is high, dependent on the intensities of this Raman is dependent on the crystal orientation, but all the peaks are present in both the cases, all the peaks. And you can see the intensities differ. And this is purely because of that, what I was talking about, that it is highly dependent on how you incident the laser light and how you collect the laser light. So it's a polarized Raman spectra which has been recorded here. And now when you do the temperature dependence, you can see that there is no change happening. It is more or less remaining the same. There is no new peak appearing. So there is no phase transition in the system at all. Usually, so we know that when you change the temperature, frequency changes in this fashion. And FWHM line width also changes in this fashion. So the frequency actually increases and FWHM decreases in the system. This is well known in Raman. Now, earlier, we had actually done iron doped, so yttrium ferrate, where the B site was actually doped with magnesium, and that shows a spin reorientation transition. And this was shown in our earlier paper that when the reorientation transition happens, there is a sudden change happening in the frequency as well as in the FWHM. And that basically tells you that spin reorientation transition is there. So with that idea, we actually looked at the frequency dependence of the asymmetric modes, B2G and B3G, I told, are asymmetric modes. So when you look at it, you see the Néel temperature transition happening. So we would have expected the frequency to increase and continue on while you see a sudden change. And that is a clear indication of a change happening in this system. So you can see that both the modes, B2G and B3G, are showing a transition around 300. And now I go with the A plane and then go to the B plane, exactly reversed behavior. It is decreasing and then increasing, absolutely reversing the order. So this is the signature of an anisotropic behavior. And Raman is able to pick up this anisotropic behavior because the magnetization is shifting in the two planes, A plane and B plane. It is shifting from one plane to another plane. The reorientation transition is happening in that direction, and that's why it is being picked up. And we can also see the lifetime also affected at 300 Kelvin. And you can see for both A plane and B plane, sorry, it is absolutely, this is for the A plane. whatever is happening in the B3G is happening just like what is happening in the B2G, and B2G is happening exactly like B3G in the case of the B plane. So it is clear opposite trend is shown, which suggests that the 310 is a spin reorientation transition where anisotropy is very big part, and this anisotropy is the reason why the gamma 3 is stabilized in the system. And so Raman was easily able to distinguish this one. Now, to show that it happens only in the anisotropic, that is the anisotropic mode. So we have taken the AG mode, which is a symmetric mode. And you can see the symmetric mode does not show much change around the 300. You can see in both the B and A planes, it doesn't show much change, but it shows the Néel temperature transition. So this is a very interesting experiment where we can see that the anisotropic peaks, anisotropic behavior is shown by the asymmetric modes compared to the symmetric modes. And that's very easy. Another interesting thing in Raman we can see is magnons. Magnons are nothing but spins which are actually showing precision, and that can actually show a wave phenomena. And that is very important in our experiments. So here you can see that again, polarization dependence is there. When you do a different polarization on the system, below the 300 Kelvin transition, you see the appearance of the magnon. And it is also dependent on the A or B direction in the system. And you can see in A plane and B plane, this magnon appears only after the 300 system, and above the 300 temperature, it is disappearing. So this is basically very important that Raman just doesn't look at only vibrations, it also looks at the magnetic excitations also. So that's the power of Raman. And so we can actually understand that these are indeed, because, and this is a ferromagnetic behavior, which is the reason for that reorientation is bringing in a ferromagnetic component into the system, giving you the magnetization. So in general, we have been able to show this reorientation transition is mimicked in Raman, and it gives you a microscopic picture of how it is actually happening in the system. And you can actually use such systems for studying even magnetic systems. This is one example I have shown. Most of the people working in solid state chemistry actually work with these kinds of systems, and I am just impressing upon them that there is a wealth of information you can get from the Raman experiments. With that, I will stop my talk here and ask you to give ask questions, and I would be very happy to answer them. I would like to thank all my students who are the reason why I can actually give these talks. These are my current batch of students who are present here, and they are the reason for these experiments which I showed you here. Thank you very much for your attention.
Participants, now the session is open for the discussion. If anyone would like to interact with Professor Chandrabas, please unmute your microphone and you can interact.
Good morning, sir. I have one question.
Yeah, Vibha,
am I audible? Yeah, thank you, sir. How Raman spectroscopy can be used to detect drug DNA and drug protein interactions? Can it be used?
I didn't show that example in mine. I have done a lot of studies on that, because even what happens is that proteins, there are 2-3 things which we can actually look at it. So one major important advantage of Raman is that it doesn't require you. Okay, let me start from the beginning. A best way to find out how a drug is binding to a protein, you can find out in 2 ways. One is you do X-ray crystallography. So you take a protein, crystallize it, then you co-crystallize it with the drug. So when you have the co-crystallization with the drug and without the drug, you know where exactly the molecule is sitting. Then you do MD simulations. So then you can know what are the interactions. So you know which is the groups which are associated. And subsequently you do mutagenesis. That means you do the mutations in those proteins, amino acids. Then you know that it doesn't bind. So you have actually found out the binding site. This is a normal method of doing it. But the biggest challenge in this is to produce the crystal. Yeah, one minute. I'm just answering this.
How Raman spectroscopy can be used to detect drug DNA and drug protein?
The question is coming back again. I don't know why. There is a echo or something like that. Okay. So what I wanted to tell is that in the case of Raman, you do not need a crystal. So, and I told you Raman is like a fingerprint. So if I have a protein in a particular configuration, then my Raman spectra will be the same. If I change that environment, immediately the protein spectra will change. Now, if I put a drug molecule, I can exactly know which are the amino acids which are getting interacted from that. I do an MD simulation to find out whether that is the binding site which is there. So I can do a docking study and MD simulation to find out whether it is there. Now, if these changes are happening, I can actually do a mutagenesis on this and find out whether if I mutate it, whether the drug is binding or not. And that is the method which I usually use for actually finding out how the drug binds to the protein. We have been very successful. We have done this in the case of P300, which is a very multifunctional protein. We have done this for kinases. We have actually found out where the binding site is. And then we recently have done this for finding out for C-Jun proteins, where C-Jun is actually a very important protein which is another kinase, where we have actually found out how to find out which is the better drug. So if I do a change in the drug, whether it is having a better affinity or not, and how does it bind. So all these things are possible in Raman. So these are our latest work, which we have actually published. And if you have any doubt, you can always discuss with me at a later stage also. Hope, Vibha, I gave you a brief idea about how we do this. So I can do a docking study
Thank you.
and MD simulation.
So any other questions from participants? Also, I would like to...
Sir, 1 minute. So what would be the cost of a very simple Raman spectrometer? Sir. Am I audible?
Sir, your voice is breaking.
Hello?
Okay.
What would be the cost of a very simple?
So you are asking about the cost of making a simple Raman. So
For the colleges of this type.
So basically, it would. We have developed up to lowest we have gone is up to about 10 lakhs or 12 lakhs. Okay. That is the Raman spectrometer which we have actually developed, 10 to 12 lakhs. We have been able to do it. That is the lowest. But a decent Raman spectrometer which can be used for experiments where research can be done. Those spectrometers are costing around 25 to 30 lakhs. That is the Raman spectrometers we have developed, and most of my experiments I have done with those developed Raman spectrometer, except for recently I have been actually buying a new Raman spectrometer. But for 20 years, I was building my own Raman spectrometers. So they cost around 17 to 35 lakhs. I have been able to get very good Raman as comparable to a commercial setup, which is about 1 crore, which you pay and get spectrometers. So you can develop it. There was one question, very interesting philosophical question, which was asked by Krishna Rao here. What would we as humans have missed or having difficulty in our life if Raman not discovered his theory? It's a very philosophical question, actually. Today, if you are actually looking at it, you will find that any nanomaterial, if you are studying today, nanomaterial. So in a sense, understanding the full nanomaterials itself, Raman is one of the major important things. It is the easiest way to do the experiments. The whole applications of nanomaterials wouldn't have been possible without Raman spectrometer. After 2005, you see Indian science has improved because of the nanoscience And that nanoscience improvement is majorly driven by the Raman spectroscopy. So if you wouldn't have had Raman, you would not have been able to compete with the world. Today, we are actually equal to the world in nanomaterial applications and various other things. And that is all possible because of the Raman spectrometers, which are available today. And today, in world over, people are actually using Raman spectrometer as a diagnostic tool for many diseases. And this is going to be the future. In future, they are going to actually be using Raman spectrometers for in situ studies. While you are doing a surgery, how to know you are removing the cancer tissues or you are removing the good tissues. You can actually target it. You can actually view it. You can actually look at plaques. You can actually look at where the stent has to be put. All of these things will be developed based on the Raman spectrometers. So future of Raman spectroscopy is being only improved and better once we can completely control how we do the Raman experiments. So that is the future experiments which is going to happen. So in a sense, Raman is today you can do a quick Web of Science or something. Look at all the papers. Raman is present in all the papers. All papers being published in material science, in chemistry, in physics. Raman is contributing the maximum in understanding of the system. So that's the answer for the question which was asked by Krishna Rao. Another one is Revati. It's a basic question that instead of taking IR Raman mass for organic compounds for structural identification, can we use Raman where in specific? So very good question. In principle, if I don't know anything about the material, so the spectroscopy is not taught independently. Spectroscopy is taught as a combination of all these techniques. IR, NMR, mass spec, Raman, everything is put together. There is a specific reason for it. Suppose let us say that I do not know anything about this material. I want to find out the material. One of the best ways to find out whether this material has, if it is a solid, if it is an organic molecule. If it's an organic molecule, I do a mass spec. I know what is the basic constituents. Immediately I know. Now, if I want to know these basic constituents, how they are assembled, I can do a Raman to find out what is the structure of it. And to make it better, I can always do NMR to find out what is the environment around it. So it is in combination, you can do an unknown system. But if you have a known system, if I know everything about the system, I can use Raman to identify the structure without any difficulty. If I know the system. So if an unknown system I'm working, I need to actually use all the spectroscopic tools to actually come down to understanding what is the actual structure of the system. So that is a short answer to your question.
Thank you, sir. I have a fundamental question, like a very simple question, that we generally say the selection rules. Like for a molecule to be IR active, there should be a change in vibrational energy level, or it should be.
No, actually, there should be a change in dipole.
Yeah, right. There should be a change in dipole moment.
Yes,
yeah.
Yes.
So, like it means the molecule will not observe, or we are not able to detect.
No, actually, any vibration. See, it's an electromagnetic radiation, right? It's an electromagnetic radiation. So absorption of the electromagnetic radiation happens purely because of the, so any IR vibration. So if a vibration has to be active, IR active, then the vibration should have a change in dipole moment. That means there is a permanent dipole moment. So let us say carbon dioxide is there. Carbon dioxide doesn't have any permanent dipole. But if I bend the carbon dioxide, the moment I bend, I have a dipole. And this dipole actually is changing like this, right? So if you look at the bending mode of the of your molecule, then the bending mode has a dipole which is facing in this direction because it's a vector. It has a dipole in this direction, so it is positive. dipole in the opposite direction, it is a negative. So if I plot the graph of the dipole changing with the vibration, the graph is actually going in this direction. So at the slope at the equilibrium is non-zero. So that is why a bending mode of carbon dioxide, even though it doesn't have a dipole, permanent dipole, it still has the IR active mode. Okay. But if suppose, let us say that I have a symmetric stretching. If I have a symmetric stretching of IR mode. So when I have no dipole moment, when I stretch also dipole moment is zero. When I compress also dipole moment is zero. So there is no permanent dipole. So that means it is not having any permanent dipole. So it is 0, 0, 0, 0, right? So if I take a slope at equilibrium, it is 0. That means it is not IR active. So even though the vibrational energy exists, the energy cannot be IR active. So all these vibrations have energy. In general, whenever we talk about absorption, we need only an energy level. You need only an energy level. So as long as energy level is there, if you supply the energy, it will go up to the next. But in vibration alone, this happens in the case of electrons. There is no problem. But when vibration is there, to go from this state to this state, that is not easy, because these two states are actually two different eigenstates of the vibration. And to transit, it needs to be coupling with the vibration, light. And that light coupling happens only if there is a the change in dipole moment at the equilibrium position. It should not be non-zero. It should not be a maxima or a minima. So that's the thing. So that's how the IR works in the system.
Okay, so what I understood is that for nitrogen molecule,
yeah,
because one of the vibrations changes the dipole moment. So nitrogen molecule does not absorb the IR radiations.
Correct. Even though there is a vibrational energy change,
yeah,
the excited state and the ground state are not going to be coupled by a vibration, I mean light. So they cannot actually make a transition.
Okay.
This in a simple term is because if you look at the nitrogen is NN, so it has zero dipole. There is no dipole. When you expand it, still it is NN, no dipole. When it is compressed, it's still NN, no dipole. So it is 0, 0, 0. So if I plot it as the vibrational frequency, the expanded, it is higher zero dipole, zero dipole, zero dipole. So it is actually no change in the dipole. So it is actually not going to absorb the IR radiation. So anytime the vibration is not leading to a monotonic increase or decrease of the dipole. If it doesn't happen monotonic increase, then it is supposed to be IR inactive.
Okay, sir. Thank you.
There are some questions here. But please submit feedback. Okay, that is correct. Okay, so no other questions, I guess.
Sir, I have a question.
Yeah.
I'm actually functional cell biologist. So I wonder, like, as you said, in signal transduction, the applications of Raman. But in signal transduction, the major limitation is existence of isoform protein, CGEM.
Right.
So I really wonder the limitation of this Raman spectra applications.
So actually, Raman cannot be directly used in situ right now in a cellular functions. I understand what you are asking. So the thing is that I can actually get a protein spectra, but for getting a protein spectra, I told you the spectra intensity of the Raman modes will depend on the concentration of the active species. Now, if you are looking at inside a cell, the protein content is very less. So the Raman spectra will be very, very difficult to see in that sense. So cellular activities, when it is happening, signaling is happening, it is not easy to follow that. It is not possible. And that's where you generally use either high resolution confocal imaging or others, because you attach a fluorophore, you use FRET or any other techniques to actually see those changes which is happening, because they are single molecular in nature. So you can do a single molecular experiments with fluorescence and others. So that's where it is. But when you are doing this, you cannot exactly know the molecular picture. You can only know that there is a folding or defolding or something like that is happening in the system, you can know. But you won't know what is the molecular mechanism. But if I could have done a single molecular experiment with Raman, which is what people are taking Raman to, if I can do a single molecular Raman, then I will be able to tell what mechanistics are happening in the system. That will be easier to tell. So right now we have not reached that level. We are still far away from that. Yeah.
So once we know that that particular isoform is very critical for that drug interaction, from
Correct.
that point only Raman will have application.
So Xe2 we do it. We collect a large sum of protein, and then you add the molecule to it and then see what changes are happening. And then you do MD simulations and docking studies to find out what I am seeing is verified by the Raman correctly. So I use an MD simulation and docking studies along with Raman to completely get the picture of how the drug and a protein. So I was working with Sijun only. That is a very important thing, because it is a very important kinase, protein kinase, which actually is there in all cellular functions, and anything going haywire in that will give you neurodegenerative disease or many other diseases come because of Sijun. So people are interested in actually able to inhibit this Sijun. So there was a molecule which was actually discovered as a possible drug for this Sijun as an inhibitor. But we wanted to improve it, and we were actually screening a large drug. So what happened is that we wanted to not do the full biochemistry. You do modification to the drug molecule, then try to understand whether it's working or not. So instead of that, I can actually do a screening, quick screening with Raman, whether it is binding to the same site or not. I can exactly say. And if it is binding, I can immediately say that this molecule can be worked with. So that way I have actually brought in Raman. So I can speed up the drug discovery by using Raman. So that is where we have reached now. We are actually doing that.
Sir, I am also curious to know if there are any direct applications of this Raman in cell biology, assays and all, because structural changes at cell level. So
we have actually been, so I definitely, so I will give another example, our latest work. We were working with, this is KPN1. So this is a protein which actually which cuts the DNA at a specific site. So it is a sequence recognizing protein. So it is highly dependent on the cationic species which is present, like calcium ion, or whether it is magnesium, or whether it is zinc, or any of those things. That determines what happens to the structure of the protein itself. So we were actually interested in knowing what exactly this. So if suppose I change calcium with magnesium, what was happening is that it was actually becoming promiscuous. That means it is slicing the DNA at multiple places. So we wanted to understand what is the reason for this. And from our Raman and MD simulations, what we could understand is that there is a region in EDD region was there, amino acid region, EDD region, which actually gets opened up. It actually becomes, it is not having beta sheets, but it actually opens up, becomes random coil. And this random coil formation is the reason the protein structure changes. And because of the protein structure changes, it actually is not able to recognize that sequence, and it slices it at multiple points. And wild type does it similarly. With calcium, it is very high fidelity, but magnesium with low concentration is high fidelity. High concentration, it is promiscuous. So this is something which we could actually see. So this is an example of how structure function we can actually see very easily. So Raman, we have used it.
Thank you, sir. Again, out of curiosity. So what about applications in liquid crystals?
Applications in liquid crystals, not much has been done in liquid crystal, because most of the times the liquid crystals are in itself, the phenomena which we are looking for in liquid crystals is quite different, where we are actually interested in looking at what happens to this. This is clear phase transitions. Basically, in liquid crystals, there are multiple phase transitions which happen. And it is easier to see these phase transitions in other techniques. So Raman is not used extensively in liquid crystal.
Thank you so much, sir. So participants, any other questions if you would like to ask? So I think there are no questions.
Yeah.
Thank you, Professor Chandrabas.
Yeah, thank you. Somebody was trying to ask or something? No. Okay. Right. Okay. Thank you so much. Thank you so much for the opportunity. And I hope it was useful. Your feedback form will be able to tell that. So hopefully the participants will give a correct information for me to improve and make it better and better, this kind of lectures. Thank you. Thank you so much.
Thank you, sir.
Right. See you.
There is just a vote of thanks formally just to conclude the sessions. So thank you so much, sir, Chandrabas Narayana, for your wonderful, elaborative, in-depth discussion and knowledge sharing on Raman spectroscopy on the behalf of Department of Chemistry and Biochemistry, Ramaya College of Arts, Science and Commerce. I further humbly take this opportunity to propose this vote of thanks to on the behalf of the department to Professor Nagaratna Amresh, Principal, and Mr. Prasanna Kumar, Head of the Department of Chemistry and Biochemistry, Dr. Ashley, she is the convener of this FDP, and all my colleagues associated with organizing this FDP program. And last but not the least, to our beloved participants of this program for their interest, time, and for their active participation. So I also would like to acknowledge our sincere thanks for our next speaker, Professor Netaji. He has joined in the early session of today's lecture. Thank you so much.
Thank you so much.
Have a good time, everyone. And next session will start at 2 o'clock. So please be prompt to join the session.
Thank you.
Thank you. Thank you.
Thank you, sir.
Ashley. Thank you, Vasant Bhaskara. Thank you.
Thank you. Thank you so much.
Thank you.